non-trivial. Because from there,
P group.
it's a
Right.
P group, so, okay.
Yeah, so it has to be, right? So that's probably, that's, I would guess that at the time that I wrote this, one of the key things I wanted to think about, right? So suppose. So even if you can't do the proofs and problems, it sometimes helps you out to, tell me some stuff you know about this. This is a P group. Everybody agree with that? This group prime power. What do you know about a P group? What's the big thing about a P group? The center is not triple.
Where is that proof for?
It's near the class equation. That's a corollary of class equation.
Okay,
And we
So-
can just skip that, right? Like since we already showed it.
What's it?
Like we can just state, like since we proved the corollary in class, we can just state that it's not, or it's not.
Let me tell you something about tests. If you know it, go ahead and use it, right? So what I would do is, a result like that, then put it down. I mean, I know that the center is not trivial, so write it down, and then I would get to this as quickly as possible, then worry about coming back to polishing it. Let me ask you this, what is the order of the center? What are the possibilities for the order of the center? Keep in mind, it's a subgroup of G, so what are all the possibilities?
P and P squared.
What's that?
P and P squared.
Right, from first principles, it's 1P and P squared, well, we just eliminated them, right? Everybody agree with that? So, two cases. The order of the center is order P and order P squared, right? Somebody get me through some of this mess. What does this mean? That's one of the cases.
Then it's a beautiful.
If G is a period, because what you're saying is the center is the entire group. All right. Everybody okay with that? What about the other case? What can we do? Yes.
The function has order P. So
Okay.
it's cyclic,
And I know.
and that usually is normal because it's the.
Okay, good. What do I know about the center of the group? It is normal, right? So this makes sense, right? And the order of that is
E.
D. So. If you have a group order P, what do you know about it? You can do better.
Go cyclic.
It's cyclic, that's right. And look at fancy fashion that I'm letting you use with impunity. G mod CG is cyclic, so G's. There were only two relevant cases. We exhausted them, so we're good to go. Everybody okay with it? That, what? Yes.
When we show group is well defined, do we show that like the function takes it from the domain to the codomain, or do we show that it's what you input only goes to one?
Oh, when you show, so really what it means, technically for there to be a function from A to B is the domain of the function is A. And that, all that means is everything in A you can plug in the function, right? So the square root function is not a function on all reals, because you can't plug in the negatives, right? And get a real out. Right? So it means that the domain is all of A. And it means that for every A, there is a unique output. No ambiguity. Always keep the square root function. That's why we say in calculus that, okay, we define this function on the positive real square root of X, and we always take the positive value, because if not, it's not a function. If somebody says, oh, what's the square root of 9 plus or minus 3, that's not a function, because it's not going to one well-defined place. All right, did that answer it for you?
Yes.
And that's the problem with cosets, really, because when you have functions on cosets, you're taking an entire set to something here, right? The input is a coset. And cosets have many different, usually infinitely many representatives. So if you pick one representative of this coset, and I happen to pick a different one, which is very likely, whatever you get from the function based on that representative should be exactly the same thing as what I get. Otherwise, it's not a function. It's not going to a well-defined place. Okay, other questions? What you guys had up there?
But, wait, for the cosets, like, I know there's multiple representatives, but then if they form a partition of the group, like, isn't that like, if you choose a different representative, it's still the same thing, like, it's equivalent to whatever I choose, so it's still going to the same.
Well, so here's the problem. Let me give you. See if I can get an example to illustrate this. But. Um. One thing. Actually. Oh, here the end bar means mod 3, here the end bar means mod 5. This is not a function. It's not well defined. Let me tell you what the problem is. How many cosets are there? There's 3 of them. So in the domain, one of the cosets is what I'll call 0 bar. It's this entire set. And 0, I think it's represented because it's easy for me, right? Here's the other set. Another set. Yes.
I take issue with the fact that we're allowing for like all of the different representatives for 0 bar, because doesn't C3 only have like 3 elements?
Yes, here's what they are.
Right.
Yes.
Okay, but it's considering C3 as like C mod 3Z.
That's exactly what it is.
Okay.
Right. And that's exactly, some people abbreviate it this way, but that's what this is. This is actually, this is a shorthand notation, CMOD 37.
So it's not, so we can't just consider it as an appealing group of 3 elements.
Well, yes, you can, but that's only because it's well defined.
Right.
Right? But this function is not going to be. Like so. Now, here's the problem. C5. This has more components. And I'll put, I'll know if by has a shadow. Now, here's what's the problem. Well, by the way, if I walk up to you on the street and give you a number, you know which one of these is in, or where the number lies in this one by dividing by 3 and checking the remainder. The remainder is 0, it goes here. Remainder goes here. Everybody cool with that? Same token, you could take my favorite prime, 8675309, divide it by 5, it's got remainder 4, so it belongs. Now, I know that this looks like the function, right? Because you take end to end, so to speak. But this is not well defined. Because here's, if Jim takes the coset representative, Jim takes the coset representative 0, and I apply this rule. Zero bar goes to 0 half. But if you pick a different coset representative, which that's a representative of the same coset, you and I are talking, it's different individual elements, but we're talking about the same coset, and that's what we're mapping. Where is this going to go? It's going to say, which one? This one right here. This is not a well-defined function because when I choose this one, it goes here. Whereas you choose a different representative of the same coset, and that rule gets you somewhere else. This is not a function because it's trying to tell this coset to go to 2 different places. Right. And that's why we did all that crap with the cosets. That's one of the many reasons why the first isomorphism theorem is useful. Because to start with R mod the kernel of phi and mapping it to something is a pain in the butt. Because the first thing you got to do day one is you're like, okay, we've got R mod the kernel of phi or G mod the kernel of whatever. You got to go through and you got to make sure the dang thing is well defined. When I proved the first isomorphism theorem, that took care of all of that. If you have this function from G to whatever, then there is an isomorphism from G mod the kernel on the image, right? And that's actually saved you a lot of work that you may not realize it has. Okay, I think there's. Okay, is that yes?
Could you have a function from an abelian group of order 3 to an abelian group of order 5?
Yes, zero function. That's the only one that will work. Because if you take that abelian group of order 3 and you map it to the abelian group of order 5, the image has to be a subgroup. So the order of the image can be only only 1 or 5, right? And it certainly can't be all 5.
So it could be a function, but it wouldn't be a homomorph.
No, that's a homomorphism. From any group to any group, you have the homomorphism that takes everything to the identity.
Right, but you could construct a function that is not a homomorphism from the abelian group of order 3 to the abelian group of order.
Yes, but I hesitate using that verbiage because it sounds like you're doing something when you say it's a group. Really what you're doing is you're constructing a function from a set of order 3 to a set of order 5.
Sure.
And that's easy peasy lemon squeezy. Right. Yes.
Spring 2021.
Spring. Okay, let R be a ring, so I'll read this and we'll write down some of the details. R is a ring, I and R is an ideal. And S in R is a subring. You show that I intersect S is an ideal of S. Okay, so. Alright. So. I don't seem to have said anything other than that's a ring. An ideal. And S in an R is a subgroup. Show that I intersect S is an ideal of S. Okay, so let's go through this. Certainly. I intersect S is a subset. And that doesn't require anything fancier than 31. It's just a subset, right? Okay, so we've got a subset, and I guess it's not empty, right? Because both I and S contain 0. So at least you got that. So what do we need for the subset of S to be a subring? But it's scary because you start thinking, oh my God, it's multiplication, it says blah, blah, blah. Most of that crap you don't have to worry about. How come? You already know that S is a ring. So all the stuff about the distributive property, the fact that multiplication is associative, all that stuff is already done for you. So let's get down to brass tacks. What do we really need to do to show this guy is actually an ideal? What two things do ideals have going on? Okay, let's take this one at a time. There's a subgroup. Notice that I and R is an ideal. And S is a ring. So I and S are subgroups of R. I agree with that. Because an ideal first and foremost is a group. And a subring is a group as well. And of course, our goal is, if we're going to show that I intersect S is an ideal, first we've got to show it's a freaking subgroup of S. That's a subset of S. Why is it a subgroup of S? Don't make this too hard. What do you know about the intersection of two groups? S. S. Because we know already that the intersection of two subgroups is a. So this is the intersection of two subgroups of R, and it's contained in S, so it has to be a subgroup. Any questions? Okay, got it, subgroup. I'm sort of halfway there. What else do I have to do? What else makes this an ideal? It's got to suck, right? And since we're talking about ideals, it's got to suck from both sides, right? It's got to be a right. So ideal. So need to show for all alpha and I intersect S and S, let me say X and S. X alpha and alpha X are still in S. This is good enough to show that it sucks from both sides, right? Because this shows when you multiply anything in I intersect S by S on either side, it's still in there. Everybody okay with that? Okay, yes.
Isn't for ideals, it's an element of the ideal? Or. Like, it's IR, RI is contained in I. So why is it not an element of the ideal? Yeah.
Oh, no, you're absolutely right. She called me a mistake. This, the first thing is always gonna be true. She's right. It's gonna be an I intersect X. I was slow. Because it's the ideal. She's right. It's got a second into the ideal. Okay. Notice that since X and alpha are in S, then X alpha and alpha X are in S. Because S is a subgroup. So in particular, it has to be close to multiplication. Everybody agree with that? So it doesn't matter what order I multiply, X alpha, alpha X, they're both elements of S, they kind of need, right? Also, as I in R is an ideal, and X is in S, which is contained in R, then X alpha and alpha X are in I. Because I is an ideal of R, X is an element of R, so it sucks that X in for both sides into the ideal. So look, X alpha, alpha X, they're in S, X alpha, alpha X, they're in Y, X alpha, alpha X, I intersect S. And there you go. Subgroup sucks things from the ring in for both sides, it's an ideal. Questions on that?
You just go over like the last one.
So you're okay with this? Okay, so we know that these products in both orders are in S. Now I want them to be in I. Now I is an ideal of R. That means anything in I, namely alpha, sucks in everything from R from both sides into the ideal, right? But X is an element of S, and so it's an element of R. So when I hit, since X is an element of R, when I hit X on either side of alpha, it's got to be sucked into I. Right? So this pair is both in S and in I, so it's in the intersection. Right? Is that clear? Okay. Yes.
I have two questions about ideals, and I think the first might answer the second. So if I is an ideal of R, like wouldn't I be an ideal of every
Subring?
subring?
No. The problem is it may not be contained in the subring.
Okay,
But and this brings up an important point. That's why I had to intersect it. Because yes, I naked by itself would be an ideal of S, but it may not be contained in it. And so we intersect it down to the piece that's in there. And that's an ideal. So the spirit of what you said is correct.
okay, then yeah, that answers.
Yes.
Is any subring contained in an ideal also an ideal?
Any subring? No.
Right, because like, the
No.
R is itself an ideal of itself, like a ring is an ideal of itself.
No, because so for example, an interesting example of an ideal is the whole ring.
Right,
And so what you would say is any subring would have to be an ideal of the whole ring.
right.
And just take a ring, this is a field, take the real numbers. And look at the subring Z, that's not an ideal at all. Because the ring's a field, it's only ideals for zero in the whole ring. Other questions? Yes.
This is on the same exams in 2021.
Yep.
Question 5C.
5C,
Yeah, show that if A is a zero divisor, then XY equals 0 for all XY's R.
you know what? This is not a good problem out of context. So I should probably go through the whole shebang. This was the magical mystery to the problem for this exam, apparently. So here's the situation. Suppose R is a ring of P elements, where P is a positive prime integer. So R be a ring, order of R. So suppose I have a ring that has exactly P elements. I can think of one, C mod P, right? Let's see what this problem says. Show that as a group, R plus C. Don't let this one intimidate you. This one should be pretty easy.
It's because it has a order and
It is prime order group. Okay, you just finish with that one. Right, okay, so there's step one. Number B, show that R must be commutative. Goodness, I'm gonna do that.
when I ask that, do we have to show that R, like state that R is the cyclic, like as a group, and then state that it's commutative as a ring?
Well, see, that's, so you already know. As an additive group, it's cyclic, so it's abelian. But what this is saying, show that the multiplication, and I didn't even tell you what the multiplication is. But actually, what's the only thing we really know? That the additive group is cyclic, right? And what does a cyclic group always have? It always has a generator, and that's it, right? So R gosh. Let X be the additive generator of this. And I'm gonna invent a notation. I don't claim that one is in here yet. Because I insist of writing a bunch of pluses. But this should be, this is just like C mod P, except I replace one with X, right? Everybody okay with it? Uh, okay. How does this go? let's think about it. Say this, suppose. Now. In X and in X. In R. I don't even know what multiplication is, but I can glean something out of it. What is this? Well. I don't know much. What's gonna happen when you multiply all these out? Every separate product is an x squared. I don't know where x squared is in this mess, but I know it's an element of the ring because it's the ring, right? And how many x squareds do I have? M, 2m, looks like I've got nm x squareds. If I go through multiplying this, I've got m of them. M of them. M of them. And I do that n times. Right? I just went bananas with distributive law. Everybody agree with that? M of them, second one, M of them, and it's all x squared, so it's all not too bad. So this is really n times x squared. Did it matter whether I did the n and the m first? This is the same thing, isn't it, as x plus x m times x plus x n times. So R is community. And I would have accepted on the exam a good, less precise argument as well. Everybody okay with it? Because basically, this read is really primitive, right? It's that additive generator. Basically, when you know what x squared is, you kind of know everything in a certain sense. Okay, let's keep building. Number 3. Yes.
Does that mean that if you have any like abelian group and you try to put a ring structure on it, it's gonna be commutative?
No.
No? Well, we didn't
No.
use the fact that it.
Any non-commutative ring has an abelian group structure on the. Additive part.
But so a cyclic group.
Oh, a cyclic group,
No, the cyclic groups are,
that's trickier.
we didn't use the fact that it's a prime word.
The only thing we've used prime for so far is to glean that this is cyclic, right?
Right, but if you had a cyclic group, you could construct a commutative ring over it.
Well, okay, certainly. Certainly. So run the question on me. If you have a cyclic group, then
You can construct a ring that is commuted, like the only ring you can construct is commuted, maybe?
well, if you have any cyclic group, you can put that in correspondence with Z mod, some direct sum of copies of Z mod in, and then you can use that ring during this community.
Okay, yeah.
And of course, you can always put the stupid structure on it by defining the multiplication of Z mod. Right. Unfortunately, I chose bad notations going on. Okay, so in the next, we were going to change notations. Let A and R be the additive generator for R. show that if A is a zero divisor, then X, Y equals 0 for all X, Y, and R. Okay. So instead of using A now, I'm going to use, or instead of using X now, I'm going to use A. Show if A is a zero divisor. Then, then X, Y equals 0 for all X, Y, and R. So in other words, what this problem is show in this situation, if the additive generator happens to be a zero divisor, then this has to be the ring multiplication, that is the product of any two elements. How are we going to show this? I think the problem's going to come up to this. Suppose and this would be useful, even if you can't solve this problem, you should tell me, okay, what's a constant? What does it mean to be a zero? Set it up, even if you can't finish it. What does it mean for A to be a zero divisor? It means what? Correct, and what about that something? There's a, you got a caveat on that something.
It's not zero.
Right, it's not zero, right? So then there exists R and R such not zero, such that R A 0. And of course, my order doesn't matter here because I've already proved that this group, or I'm sorry, that this ring is commutative. Now R is of the form KA, where right, because what do my elements of R look like? They're just multiples of A. KA just means I added A to itself K times, and my restriction on the K is it's got to be at least one, and it could be no. So it's really I'm saying is zero divisor of A has to be these guys, just not zero. Right? Well, this means and I claim that this means that A squared has to be 0. Why? I mean, certainly if A, it makes my dreams come true if A squared is 0. But why are we forced into that? Yeah.
It's, in here, you do that.
Right, right. But there's something specific. Actually, I'll give you a hint. It depends on the fact that P is prime. Really, if you got to go somewhere, do you have any questions I can get you?
No, not good.
Are you-
I just want to appreciate it.
What is it? There's something about P. Well, notice A squared is in R. I think we can all agree with that because it's some element. So A squared equals LA for some right? Because a squared, I don't have any restriction, I have to entertain the possibility of zero, but it's gotta be one of these P things, right? Everybody agree with that? Therefore. KL. Or I'm sorry, Ka squared. Is KLA. I'll write it back. This. Therefore. What can you say about KL? So here. A squared is LA, KA squared is KLA, but that's zero. So what can you say if a multiple of A, and by multiple I mean adding it to itself, that KL tells you how many times you gotta add A to itself,
P divides K.
P has to divide KL. Everybody agree with that?
We really, or how did the,
Well, because we know that KL, if you add A to itself, KL times, it has to be zero,
oh,
right? And so that means it has to be a multiple of P, right? Now, P is prime, and it divides this product, so what do we know? P divides K, or P divides L. Well, one of these is impossible.
it can't divide K. It's
It can't divide K. Look where K is, right? It's between 1 and P minus 1. E does not divide K, therefore E divides L. Right? And what is this bias? This means that A squared equals LA equals L is a multiple of P. So A squared is zero. Everybody agree with that?
How can you divide L is. Is less than.
Well, it can be between here and here.
Oh.
In fact, you're right. Given my parameters here, it's the case that P divides L, and given where L is, it forces L to be zero.
Oh.
So actually, Sophia's right. If I had paid a little bit more attention to myself, what I've written is correct, but it might be misleading because it's more general than that's to me. P divides L, and I know that P is in this range, so L is zero. I can do it. And now we've got it. Because let X and Y be an R. Then I don't know much, but I do know that X equals CA and Y equals DA. Right. So XY equals CA DA. And we actually have a theorem for class that says this is CD A squared because C and D are integers. Which is C because they students. Right. So the multiplication is trivial. It says. Show if A is not a zero driver, then R is a field. This one shouldn't be bad. Now suppose let's suppose that A is not as good as. What is that limits? I claim that no non-zero element is a zero class. Right? I claim only zero is zero class. And the proof of this is very similar to what we did. Suppose C A and D A are in R with, in this case, notice I picked C and D so that neither one of those elements are zero. Now, well. This is and our earlier work, we know A squared is one of the elements in the ring that's not zero, and that's what this is. So I get zero equals CD A squared, which is CD KA, which is CDK A. Right. So I have C D K and 0. So what can I say about CDK? Must be a multiple of so P divides CDK. Well, P is prime. So this implies P divides. I'm sorry. P divides C or P divides D or P divides A. And as Amy Winehouse would say, no, no, no. So there's your contradiction, right? So no, non-zero, 0 point. Right here, then. We have a result from class that was put out several forms. If you have a finite ring, which we do, every element is either what? I remember. A unit or a zero divisor. So as R is finite, all elements not zero divisors are units. So are units. Because nothing other than zeros is zero divisors, that means everything has to be a unit, so it's. So really, what this says, if you want to put it pipe and smoke it, is you have a ring that has P elements, where P is a prime, two things can happen. Number one, it's the zero ring. Well, it's just C mod P additively where the multiplication is X, Y, zero for all X, Y ring. So the Sylow ring, which you can always do. And the other one is C mod PC. That's it. Okay. So you originally asked about question C. Did that get you over the hump there?
Yes.
Okay. Other questions? Yes.
Can we do number 4 on this exam spring 20?
Is this the same one I'm looking at?
Yes.
Okay. Oh, show there is no simple group of order 12. Okay, folks, what kind of tools do you think from me here? I think so. So that would seem to, it would be a moral imperative, I think, the factor 12. Right. So I should have Sylow 2 groups, Sylow 3 groups, and counting will be. This one, I think we can get away with just counting. There's a couple ways you can do this, but I think you can straight up count this. It's not trivial, but you can. Let's see, let's let NP equal number of Sylow groups. Let's see if we can find out what this is. The number of Sylow 2 groups is equal to 1 mod 2 divides what? Yeah, 3. Whatever's left over is 3. The number of Sylow 3 groups is equivalent to 1 mod 3. And divides what? 4. Good, 4. Now, I'm not gonna say never, but with these kinds of problems, Sylow 2 groups are usually the most useless because 1 mod 2 just means anything. And so if you've got one other prime in there, you're always gonna have like a possibility. I'm not saying they're never useful, but usually what I do is if there's some number of them, I use some kind of one of those homomorphism into S, however many there are. But I'm gonna kind of skip over this because this one narrows things down a little bit. So this could be 1 or 3. Not sure there. This could be. Well, like the divisors for 1, 2, and 4. 1 is always a possibility. But yeah, 4 is the only one, 2 is not, because 2 is not equal to 1 mod 3. And what I'm digging on the Sylow 3 groups, well, what's another difference between them? Sylow 2 groups. What's one thing that one might consider is better about the Sylow 2 groups? They're prime order, they're cyclic, they're very, so here's the thing about the Sylow 3 groups. They're all of order 3. So if I've got 2 of them, they're either the same group or they intersect trivially. Well, they intersect in only that. Right? And that makes it easier to count. Counting the Sylow 2 groups, who knows? Because the Sylow 2 groups are all isomorphic, but it could be a bunch of Z4s or it could be a bunch of Z2, Z2s. And they can intersect in exotic ways that make it hard for you. So I'm gonna try to straight up count. Suppose E is simple. Then how many Sylow groups will I have? I have to have 4 if it's simple. Why? My choices are 1 and 4. Why does it have to be 4? If there's only one Sylow 3 subgroup, then that sucker's normal. And so then you've got a non-trivial normal subgroup, right? So if you're going to assume simple, you got to throw this out to 4 of them. Right? This accounts for blank elements in G order 3. How many? How many?
8 elements.
That is correct. There are 8. Because there's 4 different Sylow 3 groups, right? They only intersect in the identity. The identity is common to all of them, but it's like a flower, right? Here we are. All these suckers have the identity. But there's no overlap because these are primorphs, right? Right. So, for example, if this one's over here, then this generates this as well, and it's the same group, right? Okay. So I've counted 8 elements for through this group. Yes.
Could we have worked with the Sylow 2 subgroups in this case, because simplicity gets rid of.
I'll do it that way next.
Okay.
But everybody's with me so far, right? So I've got 8 elements of order 3, right? Blank elements in G. I'm gonna fill this one in because I am not going to assume my 41 back. Right. So there's only 4 elements left in the group. Everybody agree with that? And so what's the catch here? The 4 elements left over. And we sucked out all the elements for 4 elements that are left over. Have to be a Sylow 2 group. Because the Sylow 2 groups have 4 elements. So there is only room for 1 Sylow 2 subgroup. This is a contradiction. What have I contradicted here? That's right. So I've contradicted the simplicity of G because there's only room for 1 Sylow. So I contradict the simplicity, and this gives me up here to contradict the simplicity vector, right? So it cannot be simple, right? Everybody okay with that? Do I understand that kind of thing? Now, you brought up something else. Another thing is, here's an alternate way to do it. Yeah, I don't know. Yeah, G is simple. There exists exactly 3 Sylow subgroups. I'm gonna call it set A. This is the set of Sylow 2 subgroups. I've got three Sylow two subgroups there.
Isn't the counting argument also sufficient here?
How you gonna do it? I mean, maybe, but I think if you try to count exactly that, it's probably gonna get in trouble. Because,
The CLO two subgroups are of order 4.
yeah,
You have 3 minus. You have 3 times 4 minus 1, so 9 elements are covered. And then
what do you assume?
What?
What do you assume?
Yeah, because there's only the identity overlap.
I don't. This is problematic, because this is the problem with doing the counting argument that way. Because in the previous argument, my beautiful little flowers that, you know, you guys like the horse, my flowers, nothing. We knew that there's no overlap between the group, right? But when you have the CO2 subgroups, they're over 4, right? And so if I take 2 of them, their intersection, they may intersect in a subgroup order too. Right, and so now you're in trouble counting, and there's like 450 cases, and it's just awful, right? So, probably not 450, but enough to make it be awful to test, right? But there is a way to do this, because there's exactly 3 CO2 subgroups, right? If it's simple. Anybody smell what the rock's cooking? Where am I going with this? Okay, that's right. G acts on A by conjugation. So if G is in G acts on, say, PI by G, PI, the inverse. And of course, this turns out to be one of the others, maybe even the same one again, depending on the G upgrade. But this induces a permutation, right? So when I take a particular G and I watch it act on these 3, it'll switch them around. So every G corresponds to a permutation of A. So there exists a homomorphism from G, I'll call it phi, say, G into the symmetric group on the set A, which is S. So there is a homomorphism from my group order 12 to S3. Unfortunately, S3 is small enough to where I can make A out of S. Note, the kernel of phi is not equal to the identity. Can somebody tell me why? How many elements are in G? 12. How many elements are in S3? 6. If the kernel of phi was the identity, what would that mean about this homomorphism? It would mean it is 1-to-1. Do I agree with that? And I don't know much, but I do know that you cannot have a 1-to-1 map from a set of 12 things to a set of 6 things. Okay. So phi cannot be injected as the order of G is 12 greater than 6, which is the order of S. Also, the kernel of phi cannot be equal to G. Can't be all of G, but it's switching the prime.
That makes all those, single subgroups from G.
That's right, that's right. The Sylow subtheorems say all Sylow subgroups are conjugate. This is another way of putting what you said, right? All the Sylow subgroups are conjugate. And if kernel of G, I'm sorry, kernel of phi is G, then action is trivial. Because what that's saying is everything is the identity permutation, which means every action on this leaves it alone, right? And so you can never get from P1 to P2, and that contradicts the Sylow. But her phi is normal in G always. And there's your contradiction. Because I have a non-trivial normal subgroup, which contradicts the simplicity. So that's two ways you can skin that cat. This one yields to a more basic counting argument and also this business with the permutation of Sylow subgroups.
So is doing the action, like, it's G to the conjugation, like, it goes from G to the conjugate? Or what's the, how does the action like apply to these homomorphisms?
I'll give you a concrete example. Everybody got what we need right here? So I know, because I read your homework, I know there's confusion with this, and we'll try to get this straight. So let's look at the example of what's using as note that there are 3 Sylow 2 subgroups. And I'll explicitly tell you what they are. I'm going to call this P1, which is E12, P2, which is E13, which is E2. Now, what I'm doing, so this is actually one thing. So, Sophia, I'm glad you asked this question. This is one thing that's very important in mathematics. I could say, oh, you silly people, we proved this in class, which is true. But oftentimes, when you prove it, there's a difference between that and getting your hands dirty and understanding actually how the thing's doing. And that's what we're going to do. We've been to school, now we're going to do the open heart surgery. And I'm going to show you how this works. All right. Everybody agree that these are the 3 Sylow 2 subgroups of this. So there exists acts on A, which is P1, P2, P3 via conjugation. Just like I have over there. So G acting on PI is GPI G inverse. And this gives phi from G into S3. Unfortunately, I've got 2 S3s here, right? The S3 that I'm starting with and the S3 that is the permutations of this. Right? Well, I'm going to show you how this works. I'll make a little table. We'll do it with some. That was boring, trust me on that. Now, I want to know where 1, 2 goes. This thing should be a permutation of those 3 Sylow 2 groups, right? So let's see how this works. 1, 2 acting on P1. is 1, 2, P1, 1, 2. And P1 is E1, 2. Right. So if I go through and compute all this, this is 1, 2, E1, 2, so that's E. And 1, 2, 1, 2, 1, 2. So 1, 2 takes P1 to P1, right? Right. Right. And this is 1, 2, E1, 2, which is E. And this is 1, 2, 1, 3, 1, 2. Is there there? I want to compute this one. This is 1, 2, 3. Yep. And what's that? That's P3. If I agree with that. Okay, how about 1, 2? P3. This is 1, 2, P3. 1, 2. Which is 1, 2. E. 1, 2. Which is E. 1, 2, 2, 3, 2. And this is E. 1. Which is E2. Everybody okay with that? So the net result one, 2's action did this permutation, let P1 alone and swap to P2. I agree with that. So this is 2, 3. So swap P2. Great. Let's do another one. Pick a 3 cycle. Oh, 3, 2. Let's see what this one does. Everybody go with me from this. Okay, so let's see what happens to a 3 cycle. What does 3 cycle do? Well, so I'll start doing this a little quicker here. Let's see, what does this get? 1 goes to 3. 3 goes to 1, 2, 1, and 2 better go to the 7. Then it goes. And I reckon that's P2, right? So let's see what the action of 1, 3, 2 is on P2. This is 132. E 13. 123. Which is E. 132. 12. For 3. 123. Which is E. See, one goes to one, this is. It's 3. E goes to 30. And this is E3, I guess. And finally, 132 acting on P3 is 132 E 23 123. This is E 132 23 123, which is E, and it's got to be 1/6. E goes to 2, goes, and goes. So the net effect what did we do? We took P1 to P2, to P2 to P3, P3 to P1. So we needed this one. And that's how the homomorphism works, right? We gave you some abstract proof. Do you all see how to do that now? You just go through and see how that element acts by conjugation almost, and that tells you the permutation that it's deduced, right? Questions?
All good, thank you.
So does that make sense now? Okay, other questions?
Number 5 on the false sensitivity.
Oh. Oh, okay. Is this the scrap that
Yeah.
Right. Well, don't let it do definition fully. I think this would be too bad. Oh, sure. So this is all fancy. A group is said to be meta-abelian because commutator subgroup abelian, showing meta-abelian group of some. So, E meta-abelian group. Some. Which is intimidating, right? But really the important thing is to remember, what does it mean to be solved for? What's your definition of solving? And my advice is to take the definition I gave you from the homework and all that other crap that I gave you in class, right? With the lower central city, whatever, what the business was, right? So it'll be easier. Now, here's the important, do you all remember what this is? Recall that Right, so it's deductively defined. G one is the commutator subgroup, which is sometimes written this way. Which is GG. Is the group generated by all commutators. Right. And G two is the commutator subgroup of the commutator subgroup. And so forth and so on, and in general, G n plus one is the commutator subgroup. The n commutator subgroup. Sometimes I guess it's called nth derived group. So what do? First thing is you look at the commutator subgroup, and it might get a little smaller. Right, now you got a new group, start it over again, look at this commutator group, might get a little smaller. Got a new group, take its commutator, and just repeat that process. One of two things is going to happen if you have a finite group. You will either get to the identity or you'll hit a place where you're stuck. Right? Like for example, if you ever get down to A5, you're stuck because the commutator subgroup of A5 is A5 and you're stuck forever, right? That's the important thing we've done is remember what the commutator subgroup is. So let's suppose G is meta abelian. What can you say about this?
Is it really?
All you need to know is the definition, which I gave you. And then- Let's see what this takes us. What's that? This is a billion, so its commutator subgroup is definition as G1 is a billion for all x, y in G1, x inverse, y inverse, x, y equals x inverse x, y inverse y equals identity. All commutators are trivial because this is a billion. So this is solvable in 2 steps. Commutator subgroup is a billion of the 2 or less. Commutator could be the identity. But that's why it's called meta abelian, because if the commutator subgroup is trivial, then the group is a billion, and that's an influence. Commutator subgroup is trivial. The next best thing is the commutator subgroup is a billion, which means in the next step, you're going to get the identity. And that's where meta abelian. Not quite a billion, but close enough for rock and roll, at least when it comes to solvability. Yes.
For, I think it's a central series where it says that the group is nilpotent if like. Okay, yes, so, she's nilpotent if it has a central series, but like, doesn't any group have a central series? Like, any group that has a normal.
Which definition?
Oh,
So it's
I guess it's a commutator subgroup.
yeah, because those central series are defined in specific
So these
ways.
are all commutators that are normal. Never mind.
Okay, right. So you have to build this, upper central series in a particular way.
Would nilpotent for groups and solvability for groups be like kind of the same thing?
They're not the same thing, but they are related.
Oh.
They are related. Okay.
I have a question about the first isomorphism theorem for rings. So like, for the one for groups, it says it induces an isomorphism where it's like R mod or G mod the kernel to the image of F.
Mhm.
But then, so is the same said for rings as well? Like it induces an isomorphism from R mod the kernel F to the image of F, but it's like an ideal for like the kernel.
Yeah, the kernel's an ideal.
Oh, so that is an isomorphism, or it like, we can say that it is. Another.
So it's very similar in the. To the group in the following sense. So what it says for first isomorphism theorems have. The homomorphism of rings. Then. I didn't state it exactly similar to ring theory. You did it that way. Then. There exists. Involved. In R one. Kernel P. Onto the image. This is of course a subject of T, and this is an ideal of R. P bar. But R plus kernel P. Remember, this is a new set here. And this is why this theorem kind of gets you some favors, because you don't ever have to worry about the term all the time anymore. I'm sorry, that should be phi bar, this is phi bar. And of course, when we proved this theorem, one of the hurdles we had to get over was there are different ways to represent this, right? So you might pick the representative R, and I might pick the representative R plus X, where X is null. And it's got to come out to the same thing.
So that's, and then 5R is a isomorphism.
Yeah, I didn't say that, did I? Lyricus. Isomorphism. P-bar, Marmon, Carm, that's right. Yes.
I wanted to ask about the class version and what those conjugacy classes, if you could just like review what the class version is actually saying.
Well, so it says this, if you have. G is a finite root. And. X1, X2, up to X, R say, are representatives. Of the non-central. Conjugacy classes. Then the order of G is equal to the order of the center of G. Plus the sum this is just counting the elements of G by counting through the conjugacy classes, right? So take the conjugacy class of X1, all right? You look at X1, you conjugate it through all the possible elements of G, that's going to give you some different elements, right? Great. So you conjugate X1 and it goes through some Y's, and those are its conjugates. The length of that orbit is the index to stabilize. So what this particular thing does is for every Xi, it counts how many elements are in an orbit of this. So X1 it counts that number of orbits, X2 and so forth counts that orbits. And then what's this got to do with it? If an element is in the center, then what are all its conjugates? itself only. Right? Because if you have something in the center, you conjugate it, you get that element back, right? So they just pulled this out because these are all the conjugacy classes of length one. Because everything in the center is just that its own self, its own conjugacy class. These are the ones that are a little bit longer. I could have done this over the larger equivalency classes, but every one of the ones out of the center and here would have this thing be a one. Right, because if xi is in the center, then the centralizer in G of xi is all G, and that would be a one. So if you just count that thing as one element in its orbit.
So now if you, does that mean that, this is based in like group actions, right?
Yeah, I mean, obviously.
So, is that the same as like any group acting on G? This, the length of the stabilizer of G?
Oh, that's always true for, right, so if you have a group, if you have a group acting on a set, you have an element of that set, group acting on. And the length of that thing's orbit is the index of the stabilizer. So if
So that's the magnitude of four.
E acts on A, then A is A. Then so this is the set of all, this is the orbit of A, so this is the set of over. It's just the orbit of A, where it's just everything that A can move to. And the length of the orbit is just the index of state, or yeah, the index of stable, where GA is the set of X and G, such that X acting on A is A.
But this isn't part of our coming exam. Like, it's not gonna be specifically tested on group action.
Well, you know, I mean, it all builds on itself, but I mean, if this was before the, you know, I even forget. I tried to remember when we write it down. I forget completely. I'll have to look back at my notes where we were for the first exam. So I think we were like right before the Sylow theorem, right? So the Sylow theorem sort of, I think the Sylow theorem is the first major chunk on this exam. If I remember. Okay, other questions? Yes.
The material for the second container, so.
Today in class,
Today.
but I'm probably not gonna ask you who the source of it is, so. Okay, other questions? Yes.
This kind of goes like with this question, 6 of spring 2019. It's like find the stabilizer of the element one, well, I guess it's not say you erased it, but G is S3.
Is this off an old exam?
Mhm.
Okay, so what is it now?
Spring 2019, question 6.
Okay, let GBS 3 and GX on a separate conjugation, find the stabilizer of the element 1, 2, and determine the length of the orbit. You can do this just fine. Computing it out, you might see. Good way to do it. And this isn't exactly the same problem, although there will be kind of themes that cross over because I'm not acting on the Sylow subgroups, I'm acting on G itself by conjugation. So. So. G, these are of course both on this of X3. Find the stabilizer of the element 1, 2, and determine the length of its orbit. Okay. I gotta figure this out, but I have to write it down, you know what the answer is. Might have to stabilize. Well, let me ask you this. Here's a quick way to kind of do it. The stabilizer 1, 2 is a subgroup of S3. Can anybody name something that's in the stabilizer?
Yeah.
Good, right. There's another one that's not quite as easy, but
1, 2.
1, 2 is awesome. So the stabilizer. Has E1, 2. So I can actually get. So. Have those two. But tell me why. I know that the stabilizer has to be at least that group of order 2. And there's no group that's between that group of order 2 and all of S3. Right? Because any group that contains that would have to have order that is a multiple of 2 and a divisor of 6. And the only thing that's a multiple of 2 and a divisor of 6 is 2 and 6. So if it ain't that, it's got to be the whole thing. And it can't be the whole thing. Because 1, 3, 1, 2, 1, 3 is 2, 3. So I've got no choice. So that's kind of the slick way to do it. I mean, save yourself the trouble of plowing through trying to conjugate that by everything in there, right? If you think for a minute, you get an out. It's got to be, since the stabilizer's got those 2, it's either got to be that or 2, or a group that contains the only one that contains it in there. Since we toss the entire group, it's got to be there. Okay, quick follow up then. What's the length of its orbit? 3. Because the length of the orbit is the index of the stabilizer. Stabilizer's got 2, group's got 6, so length of orbit 3. Anybody, you want to guess what the orbit is? It should go through 3 different things.
Oh, it's the identity.
No, because you're conjugating it. What are the conjugates point to?
Is it? I think it's 1, 2, right.
When you conjugate an element, remember how conjugation is a homomorphism? Remember those conjugation homomorphisms we had? When you conjugate an element, it has to have the same order as the original. Right? So what's the orbit then? What's the order of the element 1, 2? Just 2. What are the other elements of order 2? Yes. 2, 3, and 1, 3. That's right. That's the orbit. It will orbit 1, 2, 1, 3, 2, 3, in some order.
So when you conjugate an element, it must have the same order of the element to be in the orbit?
Yes, but that's not good enough, right?
Okay.
So here, let me explain some of what I'm saying. So if you have phi, from P to G, you remember us doing these kind of conjugation things? These were automorphisms. Remember that? And an automorphism, in fact, an isomorphism, the input element and the output element have to have the same order. Right? That's not quite good enough. You gotta be a little careful. It is good enough in S3, but for example, oh, I think it's probably not. The orbit of 1, 2 in S4 is this. Notice these are all elements 4, 2. Here are some other elements 4, 2. This is a different orbit. Right? These are elements of order 2. These are elements of order 2, but they're in different orbits. Right? That's actually a theorem. I think I didn't formally write it down, but I think if you're in an element in SN, then you are a conjugate if and only if you have the same cycle type. Right? This cycle type is a single cycle of 2. This is 2 of order 2. But if you have like a 3 cycle times 5, you can't do this in S4. And when I say cycle type, I mean disjoint cycles. If you're in S100 and you have 2 3 cycles and a 4 cycle and a 17 cycle and a 2 cycle, everything that you can make of that form, they'll all be conjugate. Yes.
Is it possible to have more than 2 stabilizers? Like, how would that work?
Not for a fixed element. Not for a fixed element. Right. So the stabilizer of let me see. So yes. Oh, for a fixed element, you can't have 2 different stabilizers. But you might have 2 different elements that have the same stabilizer. So if you, this is again a silly example. If you take an abelian group and act on itself by conjugation, then that action is trivial. So everything just goes to itself, right? So take any element of the abelian group, stabilizers the entire group, right? And that's true for any of the elements. So all the different elements share the same stabilizer. But if you have a single fixed element, its particular stabilizer is unique. And of course, also the stabilizer of that element depends on what the action is. So given a fixed element and a fixed group action, then yes, stabilizer. Okay. Other questions?
For also 6C, what is, can you list the conjugacy classes of G?
For which one?
Uh,
Did I finish that problem by the way?
Well, cause I think I can
You
do,
did A, but not B and C.
Oh,
I think I could do be based on?
These
Like
very
the same
similar to A.
process.
Okay, find the stabilizer of the element 1, 2, 3, and determine the length of the orbit, 1, 2, 3. What do you suppose the stabilizer of 1, 2, 3 is gonna be?
1, 2, 1, 2, 3, 1, 3, 2.
Yeah, that's right. Yeah, that's right. It's gonna be that that subgroup orbit that it generates. It's gonna be a stabilizer, and its orbit is gonna have length 2. So,
Wait, the orbit is linked.
right, because it should be 2. It's the index, so it shouldn't go through the 2, 3 series. So the conjugacy classes of, yeah, I just freaked out, stop doing that. Conjugacy classes, that's 3 of this. There's one. There's another conjugacy class. So every one of these are conjugates. This is all the conjugates 1 through 2. So S3 works out very nicely. Elements 4, 2, elements 4, 3. But here's the class equation. There's the center, right, which has one element. So let's deal with the center. If you take 1, 2, the length of the orbit, which is 3, is the index of the stabilizer. That counts these 3. If you take this, the length of the orbit is the index of the stabilizer. The stabilizer is the orb 3, so that gives you the class. So that's kind of a class equation.
So the conjugacy or the conjugacy, conjugacies classes are the orbit, wait,
They're the orbit of that particular element under conjugation.
Okay.
Right? So what happens is, if you take 1, 2, and you take every element of S3 and conjugate 1, 2 by it, what will happen is it'll go through these 3 twice, as a matter of fact.
okay, so like
Right?
one,
When you
3 is the
conjugate
same
this
as
by
1, 2.
E and 1, 2, it'll give you that. When you conjugate this by, well, no, wait, something else. When you conjugate this by 1, 3, and one of these guys, it's this. When you conjugate this by 2, 3, and the other one of these, it's that.
So the conjugacy classes aren't unique except for the element, which is this element.
What do you mean they're not unique?
Like 1, 3 has the same conjugacy class as 1, 2.
Yeah, that's right. You might think of them as representatives, right? It's not a coset, but it's like that.
Oh.
And it is a partition, right? Because what it does is it breaks up S3 into 3 disjoint pieces in this case, with no overlap. They're not cosets because cosets are all the same sizes, but these are equivalence classes. And here, there's an unambiguous representative. Here you've got 3 possible representatives because these are all conjugate. And here you've got 2 because these two.
Can you talk to, 2020, number 2?
Show if I and J are left ideals, and so is the intersection. Okay, so. What assumptions do you do, yes? Same sort of business with what does it mean to be an ideal? Only this time it's left ideal, which means you only have to check the vacuum action from the left. Right? Well, number one. The left ideals have to be subgroups, therefore. I intersect J. Is a subgroup. Great. And now it's just vacuum. So to let alpha be in I intersect J and R need to show R alpha is in I intersection. Right? And that's it. That's all you gotta do. Is show that it sucks that R into the intersection. Since alpha is in I, then R alpha is in I, because I is the left ideal. And since alpha is in J, then R alpha is in J. Again, left ideal. Therefore, R alpha is in I intersection. And there you go, it's left ideal.
Well, okay.
Spring 2018, number 4.
Oh, sure, if anyone is normal in G1 and two is normal in G2, then the product is normal in the product, is that right? Okay. Okay, here's a practical question. What's the first thing you gotta worry about here? Before you have to worry about whether anyone across into is normal, you have to worry about whether it's a subgroup in the first place, right? So please, here's what I would say. I know we did this problem from homework. I think it was through fast earlier, but if you had, let's see, if you had a subgroup G1, subgroup G2, then their direct product is a subgroup G1 plus G2, right? So let's reserve this for the amalgamate. This is just about bookkeeping, so need to show for all X in M1 cross M2 and Y in G1 cross G2. Y inverse XY is in M1 cross M2. That's what it means. And you know, it sounds like baby stuff to write this down, but it might buy you points if you get lost in the woods. At least you've shown that you know what you're trying to, where you're trying to go, right? So I need to write something more convenient the next line. Uh, I can do that as well, right? So. Lines, this is G1, G2, inverse. This is N1, N2. This is E1, G2. And this is. The price of improving the homework too. It's easy to verify. And I'm being sloppy by not using the substitute properly, but I know I've got it, so it doesn't matter.
But the order of G1 and G2 split. Or that, does that?
Oh, no,
only
no,
happen
I
for
see what you
cycles?
said, but no, they're separate. They're
Okay.
going on in different coordinates. They're acting
Okay.
independently. And so coordinate wise, this is G1 inverse, E1, G1, comma, G2 inverse into G2. Well, guess what? This is N1 plus N2 as N1 is normal, G1 inverse of N1, G1 is an N1. And as N2 is normal in G2, G2 inverse into G2 is N2. So that's what you want to show.
So when you switch the order when it's like not just when it's like a cycle?
Right, because what the direct product means is, it means I'm doing two things at once. With the direct product, what stays in the first quarter, what's in the first quarter stays in the first. It's like being in Vegas, right? Nothing ever leaves this, and it's operating independently in different coordinates, right? That's what makes a semi-direct product a little weird, because a semi-direct product, there's an interaction between two coordinates. In the direct product, that doesn't happen. They operate completely. It's like you're doing one problem in the first coordinate and another problem in the second coordinate.
And you use the semi-direct product when you have like a homomorphism or something?
Yeah, in fact, the direct product is a special case of the semi-direct product, with the homomorphism is trivial. But yeah, the semi-direct product it's got a little twist based on that homomorphism from H dot G, right? In fact, all the dihedral groups are semi-direct products, and there's a lot of semi-direct products out there.
And by trivial, does that mean like an automorphism or?
Right.
Okay.
So the semi-direct product was this. The homomorphism. Then. I think that's the order I put it in. This is the set of G, H, G, G, H, H. So the set of elements is the same as the direct product. Just every possible combination, something G, something H. But you've got this weird way of combining them. The second coordinate, you do it just like you do in the direct product. No muss, no fuss. The first coordinate, you put a little twist on it. It's G1, not times G2, but it's P of H1, G2. So the reason this makes sense, or it's in the right place, is this first element is in G. P of H1 this chunk right here is an automorphism in G. So this takes G2 and it twists it a little bit by automorphism. Now, here's what I meant by my remark earlier. One homomorphism. So let's suppose P from H to G is trivial. And let me be careful about what I mean by that. That means that phi of H is always the identity and of G. Well, of course, the identity is this is the identity function that takes everything in G to itself. So this is the function that dumps everything in H to the identity. Now, if you look at the multiplication now, this is H1 equal to G1 P of H1 2. But now this P of H1 is the identity of G. And the identity of G takes G2 to itself. And so this would be G1, G2, H1, H2. So this is, in this silly case, you get the direct product back. It's a special case. And what happens in the semi-direct product is the G piece ends up being a normal subgroup. But the H piece, not necessarily so. Because remember, one of the theorems we had is in the direct product, one of the conditions for the direct product is if you have a group and you've got two normal subgroups. So you've got a group G and you find two normal subgroups N and H, such that N times H is all of G. They're both normal and they intersect in the identity. And G is the direct product of those two subgroups, right? The semi-direct product, you only needed one of them to be normal and the intersection to be trivial, and put them together to get everything. And it's the semi-direct product. And that's what happens in the dihedral group. Essentially, in the dihedral group, what happens is the G piece is the rotation piece. And the H piece is the fluid piece.
I have a question for.
Hmm?
So I have, for 2D, I have a homomorphism from R of mod I to R mod I, like, all up. But I'm just, before I like do it all, I wanna make sure that my operation for showing that it's a homomorphism is correct. Because, am I taking, like, when do I apply the opposite? Cause I'm doing addition when I do the homomorphism, or am
Should
I?
build the function this way. From R off mod I to R mod I off.
I know I did it. Yes, cause then I have to do the kernels.
Did you show it's well defined?
Wait.
Oh, or did you do this?
Oh, I did R up to R mod I up. Yeah. And then I did I as a kernel.
Right, good.
But for homomorphism, like I have B of like R1, R2.
Okay, so we're talking about this first homomorphism right here, right? Okay, so let's write down, what did you have?
For
You had phi of, I guess, R.
oh wait, for homomorphism, do we use two elements?
Well, you probably just want to define it for one, but then when you feel it's a homomorphism, it's multiple elements, yeah.
For R, yeah, well, I got kind of confused on well defined, so I just did suppose R1 equals R2, and then I did B of R1. Did you just? Yes, I did pi of I of R equals R plus I.
What you call it, pi?
I of I, S of I.
Oh, yeah, and then I did phi is the isomorphism. After I did the. Yeah. It's. What? Actually, I don't even, I didn't rewrite that.
Yeah, this is right.
And then, so, for like well-defined, I mean,
There's no well-defined. It's fine,
oh, okay,
right? Because every input, you've got
it just goes
well-defined
to R.
output.
Okay. And then for homomorphism, right now I have pi of R.
The
one
additive
plus-
part is not too bad, because it's just like a group.
So I just have to do like, would that turn into like R1 plus I plus R2 plus I?
This is what you wanna do. Right?
Is that the additive one or the?
No, multiple. The additive one's easier because it's no different. The opposite where you can't tell them apart without the multiplication. Additively, they're the same thing,
Okay,
right? So,
do I apply that circle one in the?
well, let's just take it piece by piece. What does your rule say? It says take this blob
Mhm.
and add 9 to it, right? So far, so good. Okay, to move forward here, what's this? How can I rewrite that?
R prime R plus I.
Okay. That's the definition of R op. I mean, this is R prime R plus I. And how can I break that up?
And then R prime plus I, R plus I.
Right. Now, how can I get this back to an op?
And then switch it, so. Okay, so I should apply the like circle.
This is, what did you call it, passive or passive, right? Because here's what you have to come up with. You have to come to that conclusion, but that's no different than anything else. That's the additive. You also need for it to respect your op multiplication. You need to be able to come to this conclusion.
Okay, I just, yeah, I did that.
And you're there.
Okay,
Other questions?
but I mean, it's the same thing this time. I see.
Oh, Fred, maybe you're not there anymore.
It's okay. It is, it's just